Hi, my name is Ryan Thompson, and these are my colleagues Noah James, Patrick Clan, and Ernesto Manzano, and together we are IoT. Our project is IoT Sensor System Design and Optimization, sponsored by TI. Our project is a two-phase project. The eventual goal is to design and then optimize our own IoT or low-power sensor system. Phase one is broken into two separate components. The first component is we are characterizing different capacitors based on their leakage currents. And the second component is profiling different batteries based on different current profiles in order to emulate different situations. For the battery portion of our project, we used a TI battery gauge in order to collect our data, and we did a couple of different tests. The first was a pretty simple constant load test. We simply discharged the battery across a resistor and tracked the voltage and thereby the current. And that's this graph that you can see on the bottom right over here. And this is just kind of like a general test for battery life. The second kind of test we perform is a constant current test. Unfortunately, we did not have access to an electronic load, so we had to design our own circuit in order to accomplish this, which was just essentially a current sink circuit. And this more closely emulates like a digital load rather than a general analog load. And then the third kind of test we performed was a pulse load test using the same circuit I previously described. And this is more close in line with what we would expect from an IoT system, where it's off for a long period of time and then has spikes in current while it's either sensing or transmitting data.
Okay, so for the capacitor portion of the project, the task was to design an automated system that's capable of characterizing a large amount of capacitors in regards to their leakage current. So what we did was, you can see on the bottom right, we have a graph which shows the relative leakage current between different capacitor values. And to achieve this, what we did was we created an automated system using relays and LabVIEW, to also using a National Instruments MIDAC to systematically control the charging and leaking of the different capacitors. So leakage current is a phenomenon that arises due to the non-ideal construction of the capacitors, where they have an insulation resistance. And the insulation resistance can essentially be modeled by a resistor in parallel with a capacitor, where a small amount of current always goes through. And therefore, using our system, we are able to characterize the leakage, the insulation resistance between multiple different parameters, including the manufacturer of the capacitors, the dielectric of the capacitor, and the voltage rating, amongst others. And this is important because many IoT sensor systems are battery powered, and using the, mostly the capacitors are going to mostly be used for decoupling. So we want to be able to optimize how much battery life we can gain between versus the amount of leakage current that we increase by putting more capacitors in parallel with the battery. So if there are any questions?
How do you explain that noisy yellow graph that we're seeing here? I mean, that's not what you would predict based on the simplified model that you described, right?
Yes. So we are using a Keithley picoammeter 480, and it is rated to a certain amount of input capacitance. So to overachieve that, to overcome that issue, you have the ability to put a compensation capacitor between the output of the transimpedance amplifier that's inside it with the input of the leakage current going inside. So the system for larger capacitors takes a longer time to settle. And you can see on the graph that the small capacitor values settle to a pretty constant value relatively quickly, and the larger ones take a longer time for the whole system to settle.
No, but what you just explained would not explain the random nature of things, right? It could explain why the rate may appear different. Notice how random noise-like it appears, right?
Yes, we are still working on also improving the stability of our measurement system.
Was it shielded? Because here's what I'm thinking. You measured very low levels of current, right?
Yes, correct.
And you were probably in an open environment where currents induced by even nearby phone chargers or whatever
Yes.
may have been significant with respect to what you were trying to measure.
Yes.
So your like signal to noise ratio must have been really bad. And
Yeah, so we're still working on trying to improve it. When we take measurements, we try to make the area as clean as possible so we don't have like any electronics nearby the system. that we can, as much as
It's
we can.
hard. It's really hard.
Yeah. It is.
You know,
Yeah.
you probably have to shield that, but, you know, at least be careful about not actually reading into that and thinking that that's real, okay? That's, because it's not.
Okay.
It's dominated by the noise. You could kind of see a trend, but it's dominated by it.
Any other questions? Then that's perfect timing.